Before I start, is everybody who's here was present at the previous talk I gave, or are there some new people?
I I wasn't at the previous talk. I'm a postdoc at Michigan, and my mentor gave me the link for this.
I see. Well, it's not a big deal. I'm not going to spend any serious time going over the same material, but I just going to summarize it. So I just.
Okay.
So.
I have a background in engineering and statistics, so I think I should be able to follow along, spectral estimation and so on.
Okay. Another question, I'm going to talk about something called the Wold decomposition theorem, or the Wold decomposition, WOLD. Herman Wold was a Swedish econometrician. Raise your hand if you've heard of the Wold decomposition or theorem, or learned it in class, or taught it in class, or whatever. So. Okay, so I see a few nodding heads, and good. Anyway, might as well get started and check out the sharing business. Okay, let me try to get rid of some junk on my screen. Okay, can you see the opening slide? Okay.
Yes.
Okay, great. But it's not, there we go. This is a rough outline of the topics I'll cover. Probably may not get to the last two. It's sort of a little tiny foray into group theory, which I know almost nothing about, and I'm probably over my head, but we'll see how that goes. So. Just to review the idea of a periodogram, we talked a lot about it last time, and I pointed out the standard model that representing data as the sum of a sine and a cosine term, a sinusoidal variation with the famous Loam phase shift to make things easier and to get some better statistical properties. The thing I did since then is to essentially make up this table with this approach of either maximizing the likelihood based on this model, or marginalizing the likelihood in the Bayesian sense and getting a posterior, and using that as the periodogram. You have several different ways of getting a periodogram, and it boils down to 5 different versions. And I think this underscores the notion there is no the periodogram. People talk about the periodogram of data, or, and in some sense, if you're trying to estimate the power spectrum, it seems unique, but there are lots of estimators, and here are 5 of them. Maybe there are more. In this table, I don't know how easy it is to read, but the names are the Schuster, just plugging the sample times into the Schuster periodogram, just ignoring the fact that their times are not evenly spaced. That normally, remember in the FFT and so on, you assume evenly spaced time, but just sort of dumbly sticking the times in, you get a reasonable periodogram that's called the Schuster periodogram. But these other 2 techniques, with and without the phase shift, the phase shift theta is sort of an optional. And when that's used, I call it LS for Loam, and I forget the second author, but anyway, it's these 5 different things. And all of them are combinations of the inner product of the data X with the, with the trigonometric functions. C is the cosine, S is the sine, and T is the cross product. And the coefficients of those data inner products are these other factors which are somewhat complicated but straightforward, but sort of trigonometric coefficients. And so all 5 of these are different, have different properties and so on. But what I found in practice is they're very similar. Nominally, the things with the Loam phase shift have better statistical behavior. They recover the same exponential statistics that the evenly spaced periodogram has. But I've sort of discovered that even that is not such a big deal, that in ordinary circumstances, the difference between the distributions of the other periodograms that don't have the Loam shift are not that different. And there's actually a paper discussing that I forget, I don't have the reference here, but anyway, and then this is just to, like I talked about a lot last time, extending this to higher order, two sinusoidal components, and you get a similar collection of periodograms, double periodograms that are functions of 2 frequency. And here's one example, and I was hoping that that David would be here. I don't have the list in front of me.
David is here.
Oh, he did. Oh, great. Okay.
I'm here.
Perfect timing. This is the issue of the singularity along the diagonal, and you pointed out that that should be straightforward. That should be just the 1D periodogram. It's a nested model fitting thing, and I discovered. I think I was thinking about this whole business from the wrong point of view. I was thinking from my numerical experience that when you get close to the diagonal, the periodogram has a smooth dependence. So I thought, okay, well, the best thing that is, or I was looking for something that didn't show up as a singularity there, but that's probably just the wrong idea. In fact, from the point of view of the nested modeling, it's a likelihood ratio situation. Anyway, I'm not saying it very well, but the plot on the left is similar to things I showed last time, but putting the 1D periodogram along the diagonal, and you see that there's a jump there. In the plot, it sticks out as something going on the diagonal. On the right are some slices, one horizontal and one vertical slice at different locations, showing when that slice intersects the diagonal, there's a discrete jump. So I guess this is the answer to. I was looking at it wrong, and this says, okay, for example, in the lower right, that strong peak at a given frequency, that's in favor of there being a single component there, because the likelihood ratio to one component versus 2 components is very large at that point. So my averaging across the diagonal to smooth it out was just a wrong-headed thing. Does that make sense, David? Is that what you were trying to tell me last time?
Yeah, I'm still a little puzzled by the fact that there's such a jump, but it is a funny, what do you call it, function of the 2 frequencies. So I'd have to think about it a little bit.
Well,
but the basic idea that the diagonal where the 2 frequencies are equal, that must correspond to the two sinusoids collapse into one, is exactly what I meant.
Yeah. No, I think that's right, and so I'll think about this some more. But this makes sense. I did some fiddling with the numbers, and I got a better fit, so to speak. I got the jumps to be less big if I introduced a factor of 2 into the diagonal periodogram. Is there any wiggle? Is there a factor of 2 when you do a likelihood ratio between 2 components versus 1? mean, maybe that's a dumb question.
No, I'm just trying to think about. I mean, usually, I mean, what you're plotting sh- in an ordinary problem, what you're plotting is the joint likelihood. I mean, you're marginalizing out these other parameters, or integrating out these other, or max optimizing out these other parameters. But I guess maybe that's it. Maybe because of that optimization over the amplitudes and things like that, it introduces this strange artifact. I'd have to think about it. I mean, ordinarily, if you're doing like a linear regression model and you wouldn't expect any kind of factor of two or anything like that. But
Yeah, yeah, I didn't think so, but
uh,
okay, well, some more thinking about that for me, but okay, and then Vinay, here's uh, this was I don't know whether to call your suggestion. Um, Anyway, it led me in sort of down a rabbit hole that I crawled out of um, um, fairly late. But what you mentioned was that, for example, at the bottom, well, this isn't the best plot, but remember the 2D plot indicated that there might be two components to the sunspot number periodogram. And what about the beat frequency between those two? Well, I worked it out, and it's fairly long, and it's comparable to the time scales of the so-called minima, the Maunder minimum, and there's some other, I forget the name of it, another minimum. And so, roughly speaking, that's a great idea. And I went off on trying to find, for example, the three major peaks in the triple periodogram, and identifying those components, sinusoidal components, and then evaluating them and extrapolating back in time before the data. The data I fit on was the sort of modern 100 and some year old data, but you can extrapolate these models, these triple sinusoids back in time. And the first time I did it, I almost started buying tickets to Stockholm because it seemed that's almost uncannily predicted the times of the historical minima. But then I discovered I was making a coding blunder, and the whole thing evaporated, and it didn't work out. So anyway, the reason I'm showing this plot is to point out that if you look at the raw plot of the sunspot numbers, I don't have it, but it looks more like the absolute value of a sine wave rather than a sine wave. And I think that's characteristic of any number plot. And so I thought, well, why don't I use for the basis functions, instead of the sine waves and cosine waves, the absolute values of them, which of course the frequency is then twice as big. And the top plot is the periodogram based with the absolute values of the sines and cosines as the basis functions. And for what it's worth, it shows a lot of detailed structure. Whether that's real or not, I don't know. I don't know what to say. But
I would, one quick comment about that
sure.
absolute value thing. I think it makes sense from a physics standpoint, because what happens at the end of each cycle is that the magnetic field flips and then comes back again. So if you're looking in terms of the field, it is twice as long as the 11 years. The cycle is 22 years. And the period.
Right, but what I'm thinking of is goes the other way. It makes the frequency twice as high. So the period half
and
as
also the functions have quite a different shape, right? If you think about what a sine curve is, and you take the absolute value of it, because you center at zero, right? You subtract off, you mean center the
no,
light curve.
I don't, but that's another story. I don't subtract the mean. I have an aversion to subtracting means for various reasons. But sorry, if that's inappropriate in this discussion, go ahead.
Oh, no, nothing's, yeah, no, I mean, so you fit I guess the numbers are all positive. So they go, but the sign, if there's no offset in your model, right? So it goes down to zero when the sine curve is zero. I guess the cosine curve keeps it from going to zero.
Well, depends on the phase.
Okay, so if you don't take the absolute value and you don't have an offset, the sinusoid has to go positive and negative, right?
The sign does, but then that's the main difference. I have to admit, I don't want to get too deep into this because there's a lot of things that I just tried in a Mickey-Mouse way, and I don't even remember the details. But but it just struck me that the visual appearance of the curve looks more like the absolute values of the sine of the sinusoidal functions, and so maybe you could make use of that, and maybe this is an indication of it. But sorry, go ahead, David. I didn't want to interrupt.
No, I'm fine. Yeah.
Okay. So sorry if I may complete the thought. So if if you look at the solar cycle numbers, the sunspot numbers, if you're saying that each rise and then a drop is half of the sine wave, right? So that and the second cycle essentially, in the sine, instead of going down, flips up to become like that, right?
Yeah.
So
I see.
in that case, each increase and a peak and a decrease, that is 11 years as we measure it. So you're saying that the actual sine curve is a 22-year cycle, and that is in fact the cycle of the magnetic fields. So that is a half the frequency. So I don't understand where double the frequency comes from.
Well, it's purely, if you take a sine wave of frequency omega, take its absolute value, it now has its fundamental frequency is twice as big. It goes through.
Oh, I see. Okay, so if it's right, so what you actually observe for a 22-year period is actually 11 years if we take the absolute value. Right.
So in some sense, it's going in the wrong direction from the point of view. Yeah, you're absolutely right. The physical cycle may well be the 20 some years, and I guess there's a lot of theory to back that up. But anyway, I'm just throwing this piece of dirt onto the table, and I want to go on to something else, frankly, because
okay. Go ahead. Sorry.
No, not at all. I'm just remember that I show that this double periodogram has infinite resolution in the sense of separating two sine waves, no matter how close together in frequency they are, as long as the signal to noise is infinite. In other words, there's no noise added to the. This is a simulation with pure sine waves separated by a known amount. That's the x-axis is the true separation in units of the fundamental. It's sort of a Rayleigh parameter. And the vertical axis in the top plot, forget the bottom plot, is the estimated separation. You see it tracks it exactly all the way down to zero. So super resolution, great. Of course, in reality, you have noise and other issues. And so another sort of generalization is to go to using Larry Bredhorst notation and formalism. This is just really the same concepts, but allowing general basis functions. These G sub j's are a set of basis functions with amplitudes B sub j. They're still time functions that you can make inner products with the data and so on, but they're now functions of arbitrary parameters. And so I've actually, when I was preparing this talk, I guess I thought to myself, well, what are some other generalizations? I make a big deal about how general this is. What else? What are some other generalities? And my mind was thinking about autoregressive modeling and so on. I thought, well, wait a minute, why don't I do a time domain regression? And here's the result. This is now a basis function instead of G. I used F, but it's a time-dependent model with 3 parameters: an amplitude, and there are 2 different components, so to speak, with 2 different decay constants. So these are the famous FREDs, fast rise exponential decays, or in this case, instantaneous rise and exponential decay. And so I did a triple periodogram with those 3 parameters. And here's the result of a toy simulation. The dotted line is the data, adding together the 2 components, the 2 overlapping FREDs, the 2 overlapping sinusoids. And the big dots, red dots, and dotted lines between them are the individual components in the theoretical model, and the lines are what came out of the peak of the triple periodogram. And I was completely blown away by this, because it's well known that separating overlapping shapes in the time domain is an essentially ill-posed problem. When the overlap is big enough, it becomes impossible. But in the same sense, this is actually the same logic that's going on in the super resolution and frequency, I believe. Because your model can grab onto the 2 different components of the data and sort of model them separately. And so this counters my intuition, and I think a lot of other people, that when pulses overlap in time, like flare shapes and gamma ray bursts and AGNs and all that stuff, that you really can't. It's an unsolvable problem, but it's not. And I think this must be. Well, let me just mention 2 caveats, and then I'll ask the experts what's going on here. But the next step was to try a slight generalization where the amplitudes of the 2 different components are different. Make it 4 parameters, 2 decay constants and 2. I'm sorry. I'm mixing things up. The 3 parameters were the decay constant and the location times, the peak times of these FREDs. But an obvious generalization is to allow them to have different amplitudes. And when I did a fit with 4 parameters, it just gave nonsense, and it didn't give reasonable results. And also,
question, Jeff?
Sure, of course, yeah.
So if I understand right, so your tau 1, comma 2 is effectively tau 1 and tau 2. One of them starts at time 19 and the other at 20. Is that?
Exactly. They're separated by the minimum there could be is 1 time step in this toy problem.
And both of them have the same decay time scale, right?
Correct.
So effectively the half-life is the same for both of them.
Right.
So if you were to plot this over, let's say in log scale, from 19 to around 35 or so, you would basically be except for the very first point, you would see something that's like a straight line, because you're just adding the blue and the red curves, and they both have the same shape in log space. So I'm not, okay, what I'm trying to say is that I'm not entirely surprised that it's working, because it is sort of like doing regression in where you got one the first point that is bad, but the rest of them fall right in line.
Oh, I see what you're saying. It's sort of an accident of the fact that they have the same decay constant.
Right.
Yeah. Good point. Yeah, and that's why, and maybe that points to why there's a problem when I allow them to have different values. I beat my head against it for a while and just gave up. Was getting nonsense when I allowed that to happen. And anyway, the other caveat is that because this is the cost function, so to speak, here is a second order statistic, so to speak. This is never going to be useful for modeling acausal flare shapes, which is jumping ahead to what I'm going to talk about later. But so anyway, this is. I'm glad to hear that you're not surprised, but I was, and I'm thinking that this must be something well known, so to speak, in mixture model analysis. Where I mean, this is really a mixture model situation. You have a model where you're mixing together these two different shapes, and they overlap in time to the point where they seem like they're blended together. And ordinary, like an autocorrelation analysis or something, would remember the dotted line. Whoops, the dotted line has the noise. I forget if the other lines didn't have the noise, and that does. But anyway, the dotted line is what was the data that was fed to the algorithm, and so. Anyway, it just seems to me like this is maybe a standard idea in multi-parameter model fitting in the mixture model context, if that makes any sense. Can anybody here tell me about that? Or
I haven't come across anything specifically about that sort of thing, but I don't know, maybe.
Well, I mean, it is what it is. It's a matter of terminology, I guess. It's fitting a generalized model that separates things, not in a blind way, but in a model-dependent way. And I think you're right to point out that the success of this is at least partially due to the accident of having the same decay constant, same shape for the pulses. But okay, well, let me go on. I thought this, yeah, that was going backwards. Okay, I just quickly, I assume autoregressive processes are familiar to everybody, and moving average too, but so just to make sure we're on the same notational page or something. The simplest autoregressive model is one at the top, which in the classical approach, and by classical I mean even as in the context of the Wald theorem and so on, where you deal with second order statistics and causality and all that stuff. There are values of A for which this model makes sense and values where it doesn't make sense. The absolute value of A has to be less than 1, or the inverse, the shape. Remember the connection that this is essentially generating the thing that I just showed, the Freds. A is the decay constant, and the shape of the Fred is this exponential curve as a time thing, and it's the inverse of the autoregressive filter or collection of parameters on the left. But that inverse diverges if the absolute value of A is greater than 1. And if you play the game of characteristic functions and so on, this amounts to the finding roots of the characteristic equation in the complex plane. And in the general case where you have higher order and so on, there's a whole literature on finding roots in inside and outside and on the unit circle on the complex plane. on the unit circle, for example, a equals 1 looks like it's maybe the worst problem because it's just a constant. Just 1's going to infinity, which isn't a bell shape at all. But so here's
It's a random walk.
Yes, with a random input, this becomes a random walk.
Well, so what's Rn?
That's the innovation. That's the shock, the input.
So those are like IID errors added.
Yes. In the context of
So with a equal to 1, it's a random walk. So it's not stationary, but it's a model.
Right. Yeah. Yes. Right. Yeah. I was just focusing on the shape of an individual response to the input. Okay. Here's a quote, a little history detour. I'll read at least part of it. Consider a series of terms laid out in a horizontal line such that each is derived from the preceding one according to a given law. Suppose the law takes the form of an equation of several consecutive terms and their indices indicating the position they occupy in the series, blah, blah, blah. First difference is the order of this equation is the blah, blah, gets right. But to get anywhere, you need to know the initial values and so on. Any guess as to, and by the way, there's a little typo. I've tried to parallel the formula that we'd write today. It should be different coefficients for these two terms. Any guess as to who said this and when?
Oh, really?
Okay. Anybody raise their hand?
No clue.
Laplace.
Really? That's good.
This is a little bit of a cheat. I translated his French myself. My French is not great, but with the help of a chatting friend, I was able. Anyway, I didn't change any of the ideas or concepts. I just put it in modern language. Is what I tried to do, and I'm pretty confident. I didn't change any. But Laplace, looking at this, would say, yes, that's exactly what I meant. And I think this is just the modern view of an autoregressive process. And that's all there is to it. So, and another the thing I'd like to point out, people sometimes say autoregression is really a Markov process. Well, it's terminology, I guess, but it traditionally a Markov process means that it's a probabilistic thing, that the current state depends on the previous state and not first order Markov and not any earlier states in a probabilistic thing. But in autoregression, the dependence on the previous state is completely deterministic. The random part is here, and that has no memory. That's not any. There's no Markov behavior going on there, and so this maybe is a degenerate case where the usual probabilistic Markov behavior is a delta function or deterministic. But I think that's just a terminology thing, and I think it's interesting to separate. And now the other standard type of model is that people deal with is the moving average, which is completely straightforward. In terms of astronomical applications, it's a sequence of randomly occurring flares or pulses, but this is the formal representation, either in convolution or as this finite sum of I call these things filters, these arrays of coefficients, either autoregressive or moving average coefficients, or filters, because that's what an electrical engineer would call them, and they represent an unfolding in time of a pulse shape. And this cartoon just shows that as the overlap, this gets back to the point earlier about overlapping pulses, as you get more and more overlap between the pulses, the process in the limit becomes Gaussian, and you cannot distinguish the shapes of the pulses at all. There's no method on Earth that can distinguish. For example, if you run the first two panels backwards in time, you see a difference. You see a slow rise and a sudden decay. But in a Gaussian process, you can't distinguish the direction of time, and no method on the planet, maybe I will be proved wrong, but can unfold the arrow of time in this situation. Okay, the wall decomposition, it's a classical theorem, I guess. It's in textbooks and so on. It says that it's a restriction to stationarity. Any stationary process has an exact representation as the sum of two processes, one a purely deterministic one, and the other is a random as in a moving average. So this is the sort of a boiled down statement in discrete time on the right, which is all we deal with data of the Wold representation. It's this rather specific model decomposing any stationary process into this form, this very definite form. Little remarks. I guess when I say seriously equal, I don't know what the right term is, but this is saying the process on the left is the same as the process on the right. It's not some approximation. You're not fitting some model to it in some approximate sense. The two sides of the equation are the same process. They have all the same joint probability distributions of all orders. So it's not anything other than that the right-hand side is just rewriting in a different language of the exact same thing that's on the left-hand side. And I'm amused by, in the literature, some people think this is not a very important theorem. Other people think it. I happen to think it's great. It's the Rosetta Stone for modeling for me. But anyway, Chatfield's nice book, he says it's literally, he says it's mainly of theoretical interest and has never found any use of it. Neyman was liked it, I guess, because he pointed out it describes the structure of the most general discrete stationary process. That's exactly what it is. So let's look at it in a little detail. To me, the amazing thing, and I still don't understand exactly how this works, but stationarity gives you this very specific linear representation. You can imagine stationary is a great thing, but you could imagine all kinds of nonlinear or crazy processes that are still stationary, but according to this theorem, it has to be linear in this very specific sense, and it has to be not only linear but a clear separation of the deterministic part and the random part. So that's one reason why it's useful, because it tells you that you don't have to go to nonlinear models to treat stationary processes, although some people do anyway. So another thing that I didn't, in my statement of the theorem, I didn't add this, but it comes out of the proof and the theorem itself, is that the filter C has three very specific properties. It's causal, and that's represented by the fact that the sum K is only on non-negative times. There's no response of this filter to inputs before. There's no, it only responds generating something after the input. It's clearly of use in electrical engineering, where that's built into physical causality. C is a constant. It doesn't depend on time. In other words, the shape of the pulses is the same over the whole data interval, and C is a minimum delay. And if you don't know what that is, I'll tell you in a minute. But so it's a great picture, but there are some problems already with it. in the real world, causality is not always something that you want to have happening. For example, in domains other than the time domain, causality doesn't have the same meaning at all. And in spatial domains or wavelength or any other domain than time, causality is sort of a non-issue. There are other things that replace it, dependence on neighbors and all that kind of stuff. We already saw, we didn't quite see, but you can imagine a filter or a pulse shape or a flare shape that has no origin of time extend the Fred to a slowly growing exponential that reaches a peak and then has a decaying exponential, a two-sided exponential. That there's no origin of time. There's no point where you could say there's the input to my filter and there's no response to prior information. There's always some tail going to infinity in both directions of time. So even in the time domain context, there are some cases where causality is not relevant in some sense because you can't identify the origin where the causal input comes about. And let's see, this, and if you think about it, in retrospective analysis, if once you're given data, you don't care about causality. If you're not using the future data at a given point to model it, as well as the past data at a given point, you're throwing away useful information about modeling that point. So in a whole bunch of different ways, causality is sort of suspect. And let me skip the arrow time. There's a similar thing there. But so minimum delay, this is kind of a neat concept. There's sort of a degeneracy. If you specify an autocorrelation function, here's a toy autocorrelation function which has 5 non-zero values embedded in zeros on either side. That there's not just one shape that has that autocorrelation function. There's a whole family of shapes, 2 to the n, where n is the number of points in the autocorrelation. And here's a plot of all those pulse shapes or filter shapes or whatever you want to call them that have the same autocorrelation. And the solid line is the one of interest, and the dashed line is another one. And if you do a cumulative plot of the shape, what you see is that there's one upper envelope to all of these shapes that is called the maximum delay, and the lower envelope is called the minimum delay, because in the electrical engineering context, for example, the power comes out as soon as it can, given the structure of the pulse. There, of all these filters that you can construct, it's the one that
Sorry, quick question.
Yeah, go ahead.
Why is there a band? I mean, why is there a difference between the maximum and the minimum? I mean, the ACF should give you the ACF.
I'm sorry, I don't understand.
I mean, I don't understand why there is a difference in the cumulative functions of the solid line and the dashed line in the middle plot.
Well, this is a cumulative plot, not of the ACF, but of the pulse shape.
Right. So from the middle plot, right?
Yeah. And so it's a simple matter that, I mean, maybe it's a little surprising that there's a unique upper envelope that's above. Well, let's see. It's interesting. It's above all the other.
I guess what I'm asking is, why is there a deformation in the shape of the CFN?
Why is there more than one curve?
Yeah, why is there more than one curve?
Oh, it's I don't know how it is what it is. It's let me see how to say it. There's a degeneracy. If you specify the autocorrelation, Think of it in terms of second order statistics or something, or it's like the power spectrum where you specify the amplitude but not the phase. Specifying the autocorrelation doesn't uniquely identify the shape that has that autocorrelation. There's a degeneracy.
In the context of that additive model under Wald's theorem, is it?
Yes.
Oh, I
There
see.
are
Okay.
multiple ways to specify models that have the same autocorrelation function.
Okay.
But they are, I mean, to me, the part that's interesting is that it's constrained. It is that it's constrained. I mean, because the autocorrelation function is a lot simpler than the full distribution over time, right?
Yes.
Even for a stationary distribution.
Yes. I think this will become clearer as I go on, because there's a very specific way you can actually factor the autocorrelation function into what I call dipoles. There are two filters that have two elements to them convolved together that give you can factor pulse shapes or autocorrelation functions into convolutional products where each one is I call it a dipole, and the different members of this family correspond to reversing those dipoles in time, one by one, or any combination. So if you have, in this case, there are 5 dipoles, and so there are 2 to the 5th ways of combining them, reversed in time or not. So that's the origin of the degeneracy. It's the same as that they're in the power spectrum. There's a whole bunch of curves that have the same power but different phase. The phase spectrum is different. But, well, let's go on if you're still a question. So here's an extended Wold decomposition that sort of, you see, to me, the puzzle posed by how special this decomposition is. Not only is it linear in the sense that I stress among all possible, you could imagine all kinds of things, but the filter has this very specific behavior, and also I don't talk about here, but the innovation R is normal Gaussian, unit normal Gaussian. Did I say that in the, yeah, uncorrelated Gaussian process. So it's extremely special, but you could imagine in any of those generating a process that violates any one of those with a non-Gaussian innovation, for example, with a filter, a pulse shape that is not causal, that's acausal, that is a causal filter run backwards in time, or that varies over time, that varies over the data interval, or is one of these mixed delay filters here. So you could cook up a process that violates any of those, but still is stationary. And the Wold theorem says, oh, well, tough, I can still represent it with a representation that has those properties. So how can that be? How can, for example, if I generated a process that had a maximum delay shape to it, the Wold representation is going to represent it as a linear combination of minimum delay pulses. How is that possible? That seems crazy. Well, here's my attempt to answer that. I've never seen anything in the literature like this, but I think it's an obvious corollary of the Wold decomposition. And basically, you just realize this degeneracy in the second order statistics, so to speak, and you say there's a whole family of moving average representations, not just one. And the index K here is, sorry for the bad notation, K is now represents the members of the family, this family of moving average processes. And one of them is minimum delay, one is maximum delay, and the rest are mixed delay. So I think this is obviously true. It's just sort of taking this formalism and looking at the world decomposition and how it works. It's just straightforward. But it doesn't tell you how you can decide from data which one you have. It doesn't tell you how you can analyze data. And that's the thing I've been working on for a long time. And maybe I should skip ahead. Our ARMA models are combinations of moving average and autoregressive models. This is the most general causal ARMA autoregressive moving average model, where in both cases you have causality. And I think it's interesting to note, sort of just playing around with these using various representations, there are a lot of things that are equivalent to each other. Some of these are slightly different flavors of things, but you can represent obviously the basic convolutional relationship, but you can talk about, there's a lot of literature that talks about a shift operator, or the characteristic polynomial is equivalent to if you replace the free variable in the characteristic polynomial with the shift operator, you get an operator representation of the most general AR model. And if you factor the characteristic polynomials, you get this relation. And here, then it was what I was talking about. Each of these factors of the characteristic polynomial I think of as a dipole, kind of a rudimentary element. It's a first order autoregressive model on the left, or a first order moving average model on the right. And the full model is the product of those in the characteristic polynomial, but you can reverse in time any one of those dipoles and get something that has the same second order statistics, the same autocorrelation function. And therefore, if you estimated the parameters of the model with, for example, the Ewell-Walker type of approach, where you start right away taking autocorrelations of things, you are no longer able to resolve the degeneracy that this represents. So I don't know if that makes sense. And so at the bottom, there's kind of it's covered up by some Zoom junk on my screen.
We can see the stuff.
Relationship between the Fourier Laplace delay operator and characteristic or Z transform and characteristic polynomial. They're all tied together, and they're all kind of telling you the same thing about the general ARMA process. So let me see. And so there's kind of this is my Rosetta Stone that comes out of this whole viewpoint, is that all of these processes are really the same thing, and any one of them can be turned into the other by a simple inversion of the filters involved. If you we already saw that a first order AR process, if you take its inverse, so to speak, you get a moving average that is the corresponding exponential with the autoregressive parameter as the exponential coefficient. But that goes both ways. You can go back and forth, not just first order, but any order. And each of these inverses can be done one factor at a time in the characteristic polynomial factorization. So this may be confusing, but it's really a very unifying picture. These are all really the same thing. And in practice, you can actually implement this using the standard Fourier. I think this has a fancy name. Some theorem in Fourier. Anyway, it's just evaluating convolutions with Fourier transforms, and by the same token, as long as the Fourier transform of a filter doesn't go to zero, you can evaluate its inverse, its convolutional inverse, in this way. So this is a a nice package that corresponds to easily implemented data analysis things.
So does that mean that any ARMA model can be written as a moving average model or an autoregressive model?
Yep.
That is pretty cool.
It's the same model, but in practice, there's the parsimony or whatever you call it issue. That, for example, first order AR is an infinite order MA. So you might
prefer one over the other.
Yes, and maybe physical interpretation might be easier. You might like to think of pulses in time, so the moving average viewpoint is better. If you think in terms of memory of the past, a causal autoregressive model might be preferable and so on, but you're really looking at the same thing written in different language is a way of thinking of it. So I said, you don't know how to find the right member from this degenerate family of mixed delay representations, or other things that are going on that the Wald theorem kind of sweeps under the rug because it doesn't allow you to sense what's going on. Here's a conjecture that what you need to do is this first thing is called a prediction operator. This is a linear prediction operator. If k is positive only, it's a prediction operator, or the current value is linear prediction from the past data. And this is the first ansatz in the proof of the Wald theorem. You do this, set down this prediction operator and then find the best coefficients in some least square sense and so on. But there's the rub. You don't want least squares because that limits you to second order statistics. So this is now going to be, this is a conjecture, but it's going to be agnostic about what measure you use to find the best coefficients in this predictor, or in the proof in what is it? Forget one of the books I use. It has a nice proof of it where you use Hilbert space projection operators and all that stuff to make it rigorous in continuous time. But really what you're doing is projecting things. And the conjecture is that if you can construct some distance measure between the model and this predictor of the model, this generalized prediction filter, this acausal or mixed causal prediction filter, and construct some distance measure that's presumably is some average over the data, and you find the minimum of that distance, that then in the same fashion that the Wald theorem gives you the unique second order statistics representation with its causal filter and all that stuff, that if you can do this and this thing has a minimum with respect to the parameters, then putting those parameters in the predictor gives you I'm speculating that it's exact in the same sense that the Wald representation is exact. So obviously this whole thing depends on constructing a good distance measure, and over the years I've struggled with things like L1 replacing L2 with L1, and that has some ability to recover phase information. Anyway, and here's the sort of general model. This is a acausal ARMA model where you allow predictions both from the past and the future. And here's an example, sort of a success story of finding a measure that works and works for this simple case. These shapes are a whole bunch of different second order autoregressive processes where there's one causal term. Sorry, this is the causal term, and this is the acausal term. So it's a two-sided acausal or non-causal autoregressive model with an innovation that's not Gaussian but is uniform on 0 to 1. That's another thing you have to do, is to stay away from Gaussian innovations. Anyway, so a bunch of pulse shapes, some of which are time reverses of the others. The ones on the sort of diagonal are symmetric. And all of these, none of these could be distinguished from each other based on, for example, the Yule-Walker approach or any approach based on second-order statistics. But adopting a simple sparseness measure, and some of you may know sparseness is these days a big deal in a lot of analysis. Compact sensing, I guess, is one of the buzzwords. But I cooked up what I think is a interesting and, to my knowledge, unique measure of sparseness. It's a simple idea. If you have a bunch of data and you want to measure whether there's just a few big numbers and lots of small numbers that don't matter too much, if you calculate the cumulative distribution of those data points, the area under the cumulative distribution is a good measure of sparseness. In the limit of sparseness where there's only one significant data point and the others are all 0, this curve jumps up to 1 right away and is flat all the way out to 1. For a uniform distribution, you have a sort of a straight line. So the area under this curve, going from roughly a half of the unit square to the area of the unit square, which is 1, is a measure of sparseness. And it seems to be, of all the things I've tried, it's worked the best at this problem of by maximizing the sparseness of the innovation and then playing the game in the conjecture that I in the previous slide, you can actually uncover the parameters. This is a plot in parameter space where this causal autoregressive parameter is on the y-axis and the acausal one is on the x-axis, and this is for a simulation of several hundred random points in terms of the sampling in time. This algorithm is you can. Well, I won't go into the details, but basically this nails the values of these coefficients in a way that the standard methods just have no hope of doing, and with a fairly small scatter about the true values.
Can I ask a question?
I was going to say, yes, your hand is up.
Oh, sorry.
Go ahead.
Yeah, I think I thought I understood, but I think I've misunderstood this point. If you go back to the slide where you were talking about the Hilbert space, and so I think I'm just didn't pay close attention. I thought that what you were saying is that when you're solving for the parameters, the distance measure that you're using isn't just like L2, and you can try these other L1 measures. And then I thought that would mean that, you're assuming your innovation is like a different distribution other than Gaussian.
Yes.
But I think I've misunderstood. Is that what you're doing? Like you're solving for the BK under a different distance metric, or?
Right. Yes. And I wrote it in the most general way I could think of here. This F here could be the innovation. In fact, if it's just the difference between the true value and the predicted value, that's the innovation. But I wanted to allow other possibilities because basically what's going on here is the sort of slogan is there's only one way a process can be Gaussian, but there's an infinite number of ways a process can be non-Gaussian. And astronomers struggle with this in the cosmology. I'm talking about non-Gaussian initial conditions of the black body and all that stuff. But it's really an infinite space that you're dealing with of all possible distributions, and so I think you need to have a general viewpoint. But it is maybe it's best to be concrete and think of it as the different measures of the innovation that go beyond just L2, just beyond RMS statistics of the innovation. And like I said, L1, just doing the standard things and replacing L2 with L1 does recover some of the acausal information, but it's not nearly as good as the this measure here. But just as a numerical experimental conclusion. But does that answer your question?
Yeah, I think I kind of missed that this was a different measure, and I didn't read the pseudocode closely enough.
Well, it's I'm sure it's not written as clearly as it could be, but so David, did you have a question too?
Thank you.
Sure.
No, I was just going to alert you that Jamia's hand was up.
Oh, okay, thanks. Yeah, okay, now let me just quickly dispense with this. I'm not a fan of, well, I don't know how to put it, but this is a little foray into group theory because I don't think it's not as completely straightforward to construct a group, a convolution group that filters form a convolution group. Here in the upper left are some well-known properties of convolutions, and everything is fine to make a group with the possible problem of inversion of filters. And remember when I first talked about first order AR filter may not have an inverse. And so it seemed like it's a non-starter, but there's a way of dealing with that. If you take this formula with the Fourier transform inverse, that is to find the inverse of a filter as the inverse Fourier transform of the reciprocal of its Fourier transform. This gives you a result except when the denominator goes to 0. So you can construct a set of filter shapes, these A values are, just a general representation for the shape of a filter, where you need two conditions. One is you need to normalize it. You have to, the standard normalization is to have at the origin of time unit, and then the constraint that the Fourier transform never goes to 0. And it turns out that in practice, that never happens if you have real data numbers and so on, but technically you need to avoid that. But another problem with a group is that if you allow filters to be infinitely long, then even with this inversion, you get cases that clearly don't converge. That case where the first order autoregressive filter for A bigger than 1, that diverges if you let it go to infinity. But you can't, well, anyway, in a nutshell, I make an ansatz. I say, I'm going to fix the length of the filters. I pick a number. Let's say the length of your data set is, you have n data points. Let all filters be of length n. If you have a filter that's shorter than that, you want to use it in your analysis, embed it in 0. So there's no problem with fixing the length of all the filters. And then when you do this inversion, then you have wraparound. If you do these operations with some of the standard convolutional tools in data analysis systems, things get longer. But if this Fourier approach, assuming periodic replication and so on, basically things that spill off the end get wrapped around, so you can conserve the length of filters. And in practice, that's not a problem because you're embedding short filters in zeros, that what gets wrapped around is 0 anyway. So I'm just rambling on that you can repair the problem with finding the inverse of a convolution and generate a group of filters. This is for causal filters, but you can do the same thing for general causality in filters. But even more, you can generalize to ARMA models forming a group, and a few little tricks here. The element of the group is now, for example, a combination of two elements, the causal filter that represents the moving average, or sorry, the moving average filter and the autoregressive filter. And define the group operation in this way, in an obvious way, that it's a convolution of the individual AR and MA parts to it, and everything works out. There's a little trick that the inverse, you have to swap the A and the C and invert them. This is the only definition of the inverse for this way to represent things. And so not only do you have this family of autoregressive models being a group, but there's something called the generator of a group, namely an element of the group which can generate all of its members under the group operation. And any factor in this factorization of the polynomial can serve as a generator. In fact, this expression inside the pi there is the generator for this group, the autoregressive generator, and this is the moving average generator. So these two things, these two simple dipoles, generate this whole group of ARMA models in a convolution. This is sort of formal, and I think it's a nice unification of things. It shows you how you can generate things from very simple elements, and there are only two essential elements: a first order autoregressive filter or model or whatever, and a first order moving average filter or model. And combining those in various ways convolutionally, you can generate any of this family of things in this picture here. So that's all I had planned. And once again, thanks for all your feedback.
Jeff, quick question about the last point. Does that mean that any one of the members of the group can serve as the generator? I'm not familiar with like group theory.
I'm not either.
But...
Go ahead. Go ahead.
Well, I've also come across this for rotations, people talking about groups. So I'm just interested in trying to learn a little bit. I think in our case here with the ARMA group, that any one of those filters can generate all the other filters because it's a kind of a unique mapping. But like in general, is that true? And in general,
yes,
is that also the definition of the? I guess that's in general for other groups. There may not be that holds that every element can generate all the other elements, but in this case it does.
Good question. I don't know enough group theory to know if there are some groups that don't have generators. But technically, I believe this would be called a Lie group because the coefficients are continuous variables, not discrete. This thing at the bottom, think of the Z as sort of an interloper. There are two elements. There's the unity and the coefficient A, or alpha here. That's a continuous variable, but it serves as a generator. For if you consider all possible values of that continuous variable, you can generate any element of the group. So it's a Lie group with a simple generator. How what that entails in terms of formal theoretical results, I have no idea.
Thank you.
So the formal the party line is that every group has a generating subset, but that subset may be the whole group.
Okay.
So they don't necessarily have a generator that's small.
I see. Interesting. So this is sort of an extreme. It's a very small. If it weren't for the continuous nature of the generator, it's one. It's unique. There are two, but it's in terms of actually. I guess there's one element. In terms of this definition, there's one element with one dipole for C and one dipole for A. That is a unique generator, but it's continuous.
So does this mean, by the way, that so if you have two ARMA processes and you superpose them,
Yes.
they will look ARMA?
Yes. Well, yes, they will look ARMA, they'll look AR, and they'll look MA. Mr. Wold will take that data and give you a moving average representation for it.
What do you mean by superimpose them? Plop
I
them on
mean,
top of
Yeah. I mean, we see this all the time, right? I mean, we have a black hole or a neutron, a low mass X-ray binary and a disk around it, and they're both producing
But how
different.
does they will look ARMA without superimposing them, and they will look ARMA individually. What is superimposing?
Yeah, that's what I meant. I mean, individually, they would look. You
If
would
they're
have,
ARMA, they'll look ARMA.
yeah. I mean, with the different coefficients. That's what I meant.
I think what Vinay is proposing is to add the values to sum them.
Some of them, right?
To take data generated by one and data generated by the other. David, I know you don't like to dirty your hands with data, but
That's not true.
He does. We have trained him well over the past 30
ARMAs
years.
are linear processes, so
Yeah.
summing should be fine.
Yeah, exactly. And so if you add two stationary ARMAs, they're stationary, so they qualify for Wold.
If you start multiplying them or exponentiating them, Vinay, you might get yourself into trouble.
Well, okay, let's think about that.
You might.
Suppose
I don't know.
Well, take two stationary ARMA processes, multiply them together. Is that stationary? I think it is.
Stationary. Yeah, so maybe by Wald's theorem it will still be. I mean, because if one is stationary, that means they have the marginal distribution of X doesn't depend on the N. So that means you have two yeah, gosh, are they both? I would think, I shouldn't say, but I think they're still stationary.
Yeah. I once asked ChatGPT that question and it said, no, they're not I forget exactly. And its answer was complete nonsense and violated the premise of what I was asking. But no.
So if the two processes are themselves independent, how about that?
Yes.
Good. Yeah.
Then their product should also be stationary.
Yes, they have to have the innovations are in the two different ARMAs are different, and well, let's say you want to postulate that they are independent, but I don't think that's necessary. Suppose they both have the same innovation. That's no problem.
Well, I'm just saying that if they're independent, then they are. If they're independent, then that means that at every time you have a distribution F and you have a distribution G. And you take the product of those two distributions, it's going to be a distribution. And it's always going to be F times G.
I see.
So it's very simple. I don't know if they're not independent, then you have to think a little harder.
Yeah, but they've got to be stationary. There's just no way it can't be non-stationary.
Well, the question is if F1 times G1 is equal to Fn times Gn. If they're not stationary, if they're not independent, it's not absolutely clear to me that they would have that those two things would have the same distribution, even though the margins are the same, that their product would be the same.
Yeah, you're right. I think you have to do a little work, but my intuition is you'll end up with stationarity at the end. But
this is all hypothetical. Then you're going to
don't
add
you have to?
Go ahead.
Sorry.
Go ahead. Sorry.
No, go ahead, Janelle.
I was just going to say, if it's stationary, all of the higher order moments have to be fixed, not just the second order. statistics,
The
which is true for
whole-
Gaussian.
The whole
But
distribution
could you
is the same.
construct a weird distribution where, like, two stationary processes where all the higher order,
That's
like
a
I'm
good.
thinking of things like squared functions and stuff like that.
Is it stationary? You mean the whole distribution is the same? Maybe there's
Well,
different kinds of
stationary would
stationarity.
mean that the higher order moments are invariant to time. And then for Gaussians, it's simple because Gaussians are fully defined by the second order, by the
Well,
covariances and the mean.
You also have to know that it is Gaussian.
Yeah, so what I'm saying is if there's non-Gaussian distributions that have weird functions, can you like construct something? I was just thinking about now myself getting confused if two things added together are in fact always stationary if they are individually.
Yeah, what I don't remember is what strength of stationarity is required in the theorem. The best analysis Brockwell and Davis, the time series theory and methods, is the best treatment of the rigorous proof that I found. Maybe there are better ones, but somewhere in there it probably describes it. In the statement of the theorem, it just says stationary.
Yeah, so just Wikipedia says a stationary process is a stochastic process well, this isn't very helpful, sorry, whose statistical properties such as the mean and variance do not change over time. So I was thinking it was saying the mean and the variance, which of course is not nearly as strong as saying the distribution doesn't change over time. I just thought it meant the distribution didn't change over time.
For Gaussians, that because they're fully defined by their mean
Yeah,
and
but
variance.
you don't know to say it's stationary, you can't say it's automatically Gaussian. Sure, if you know it
I know
is
that's what I'm
Gaussian,
saying.
then
I'm
only
agreeing
the
with
mean and
you.
variance determine
I'm agreeing with
that
you. I'm saying
particular
that
Gaussian distribution.
I'm just explaining why Wikipedia gives that as the first case, because like for Gaussians, it's easy to confirm
It
stationarity
doesn't
just
say
by
Gaussian here. I'm sorry. That's a pretty big assumption.
yeah, I know, but I'm saying that's why they say the mean and variance, not that fully defined stationarity. I'm just saying that's like one case where it's easy to show stationarity.
Yeah, but that's a case you have to say something to say you're in that case.
Right. When it comes down to it, there's an infinite number of types of stationarity. Stationarity with respect to any statistic you can define. And you could define kurtosis stationarity, right? A process is kurtosis stationary if its kurtosis doesn't change with time. It may not be useful, but you could do that. And so this textbook thing of wide sense and strict stationarity and covariant stationarity, they're all special cases, and you just need to be careful about which one you're invoking.
Yeah, especially if you have a theorem that just says stationary.
Yeah, well, that's a good
exactly
point.
what I mean.
I'll try to figure out if I can what type of stationarity. From the proof, you can find out by looking at the proof when
Sure. Sure, yeah.
already what's involved. But it's all in Hilbert space notation, which
Doesn't make it easy. Yeah.
All right, we are past our cutoff time, so thank you very much, Jeff. This was very thought-provoking, and I certainly learned things that I never imagined. So thank you. That's
mentioned Garsh. I barely know what Garsh is, but is this any of what I've talked about relevant to Garsh modeling?
Garsh is like ARMA, but for standard deviation for the error for the scatter. So it's effectively including the building the time series of the standard deviations, with time.
Oh, okay.
So it's kind of related, but it's slightly different.
So are you or someone else going to talk about that at some upcoming?
I suppose we should. I'll try to get our student who's actually in Texas, who's been working on test analysis of to talk about GARCH. That's a good idea. This year has not started off well. There's too much going on, and we haven't gotten our act together.
Yeah.
Getting this, getting the CHASC talks going. So we'll do that soon.
Yeah, okay, understandable. So, all right. Well, thanks everybody for comments. As I like to think of these as inverse seminars. I learn more from you than I lay out. But
Yeah.
Okay.
All right. Okay, good.
Thanks,
I
Jeff.
don't know.
Well, I guess we'll
Yep,
talk soon, all of us
we'll
at some
talk
point.
soon. Yeah.
all right.
Okay.
All right.
Bye-bye. Good night.
Bye, everyone.